We're going to study a method today of finding volumes. These solids that we're going to find the volumes of are created by revolving a two-dimensional region about a line. And the line is called the axis of revolution. So if I take this rectangle and imagine revolving it about that line, what kind of three-dimensional shape am I going to create? Cylinder, yeah. And how about if I take a hemisphere and revolve it about that line, what do I get? A sphere. I should have said that semicircle, not hemisphere. Take that semicircle, revolve it around the line, you get a sphere. How about if I take this right triangle and revolve it about the line? A cone, yep. And now I'm going to take this rectangle that's not touching the line this time. So it's a little different than this one because there's going to be some empty space. What do I get? Like a long donut, yeah, or a tube. Good. So for each figure, we're going to draw one little slice. So last class we started talking about slicing and finding areas and volumes by slicing. So for each figure, I'm going to draw a slice perpendicular to the axis of revolution, and then picture that single slice as I revolve it. So in this first one, just pick any random spot, draw one little rectangular slice. Imagine it having very, very, very thin thickness. What shape do I create when I revolve that one slice around? A circle, yeah. Circle, very, very small thickness. All right, we can call that delta x. So I would get a circle. And maybe, I don't know, we'll call that r for the radius. You get a circle with radius r and thickness delta x. So for this guy, if I just pick a random spot and draw a little rectangular slice and rotate it around, what kind of region do I get? Another circle, yeah. And for my cone, any random spot, draw a little representative rectangle. When I rotate it around, I'm going to get a circle. Okay, here's my only one that's a little bit different. Take that little bitty rectangle, rotate it around. What's it going to look like? Two circles, a donut, or your book calls it a washer. So you would end up with a washer like this. If this distance, we could call that r, is that. Hey, Taylor. Okay, so here's a couple of more complicated looking examples, right? You could take any curve in the xy plane, rotate it around an axis, and come up with a solid. So here's just some curve f of x. Look at the area underneath it from A to B, and then take that whole area, rotate it around the x-axis, and you get this bell-shaped solid. And you can see that each cross-section of this bell shape is a circle. And then we could get even fancier, right? And I could use a curve as the top and the bottom of my region, right? And rotate that region around. And it would be a tube, right? Just kind of a fancy looking tube. And my cross sections would be washers. Okay, so for obvious reasons, the method that we're going to use to find these two things is called the method of disks and washers. So we either get a disk, which we were just saying it was a circle. We could call it a disk because it actually has a little bit of thickness. Just I'm just a terrible, terrible artist. This is hard for me to draw. It's got like a thickness of delta x. Call it a disk. I actually grabbed some notes there. Okay, so we're going to just take a quick look at some animations, because the hard part of these problems is like learning how to visualize what the shape is going to look like and how to build the shape from the cross sections. Okay, so here I've got just a little line here. Think of this as, it could be any curve. Right now it's just a line. I'm going to revolve it around this vertical axis of revolution. So your axis of revolution can be horizontal or vertical. Revolve it. So this would be like your representative slice. Revolve it around, and you can see we're creating a disk with a very small thickness. And we would call that thickness like delta x, or delta y in this case, because it's vertical. And then you can see this disk is just made up by rotating a rectangle around the axis. All right, and then we'll take a little look at this. So here's the graph y equals x. If my axis of revolution is the x-axis, I could say just pick any representative rectangle. So here's a little rectangle under the curve. And I want to hide that. Revolve just that one rectangle around the axis. And you get a disk, right? You get like a short cylinder, a disk. The area, the volume of that thing would be pi r squared times the delta x, right? The area of the base, which you would get by finding the area of the circle, and then times its height, delta x. So you do that for each rectangle, right? So that for maybe this rectangle, revolve that one, you get a little disk. You would find the volume of that disk. And then we do that for all of these rectangles underneath the curve and add them all up. So I'm going to show all these rectangles. Here's all the disks. And you can see that this is a good approximation of the solid that we would get just by rotating the region around the curve. It looks kind of like a pyramid. That's good for now. Okay, so I'm actually going to use that function, y equals the square root of x. We're going to find the volume of the solid that's obtained when we rotate y equals the square root of x, bounded at 1 and at 4, around the x-axis. Okay, so I'm going to draw a picture of it. There's the square root of x, and we'll go from 1 to 4. So this is my region. I'm going to rotate it around the x-axis and find the volume that results. Okay, so first thing is I'm going to pick a representative rectangle. Just any random spot, I'm going to draw a little rectangle. And we'll call maybe the left endpoint of that rectangle x, and then the width of that rectangle can be delta x. So when I rotate that representative rectangle around the x-axis, I'm going to get a disk. So I'll try to draw it. God, I'm terrible at this. It's so good. I'll just draw it 2D. Okay, it's got some width here. right? Delta x is the height. What is the radius of that disk? Whatever the height is at x, right? So this is the x value along the x-axis. And then this guy ends up being the radius of the circle. And I can find that distance by plugging whatever this x value is into the function, right? So my function is square root x. So that's the radius of my circle. The radius of my disk is always going to have a radius of square root of the x value. Okay, so the volume of my disk is pi r squared h, right? That's how you find the volume of a cylinder. And in this case, my r is square root x, and my height is delta x. So this becomes pi x delta x. So then I have the volume of one little cross section, right? One small slice of the solid that's going to result from when I rotate this whole region around the x-axis. So now I'm going to add up a whole bunch of slices. I'm going to do this at many, many x values. I'm going to have a little rectangle, and I'm going to use that to create a disk, add them all up, and get an approximation for the volume of this region. So the volume of the whole region is going to be approximated by a sum of a whole bunch of disks, and each one is going to have volume pi x I delta x, right? Because this is just an x sub I. Okay. And that's going to be I going from 1 to n. So I'll have x1, x2, x3, x4, x5 up until xn, breaking that up into n little rectangles. Then when I let the limit, let n go to infinity, take the limit as n goes to infinity, I get the exact volume of the region. So the volume of my region is going to be the integral of pi x, and instead of delta x, that becomes a dx when you take the limit. And my bounds of integration are going to be 1 to 4, because that's where I'm stacking up these disks. I have all these disks, and I'm stacking them starting at 1 and moving to 4. So when I calculate this, I end up with pi x squared over 2. We take the antiderivative, plug in the 1 and the 4. So I have 8 pi minus pi over 2, which is 7.5 pi, 15 pi over 2. Exact area created when we rotate that region about the x-axis. All right, let's watch an animation of actually rotating this thing. There it is. Okay. So first thing that can be handy. Oh, I want to move the axis of revolution. I want to be the x-axis. All right, now just revolve this thing, and it goes around. And you can see it's highlighting one disk, because that's how we end up calculating this thing. We look at one disk, find its volume, and then add them all up. Right, so we stack this one disk going from 1 to 4. Does that kind of make sense? All right, so how are things going to change in this example if instead I revolve this same region, this exact same region, the area bounded by square root x, the x-axis, and the vertical, this in pink since that's what my rectangles are. And the vertical lines x equals 1 and x equals 4. I'm going to take that same region, and instead of rotating it around the x-axis, I'm going to rotate it around the line y equals -2. Try to draw a picture of it. Here's 1. Here's 4. I'm taking the same region. But this time, my axis of revolution is this line. So what kind of shape am I going to be creating? Yeah, a ring or a washer is going to be the cross section. The whole thing is going to look like a bowl or a vase. It'll be hollow in the middle. So let's look at what the solid will look like. When I move this axis of revolution. So it goes behind, and then this is now it's in front of the axis. So it's like a bowl but without a bottom. And then here's my representative washer. I'm just going to watch it sweep through so you can see I have this washer is my cross section all the way up. And so I want to find the volume of this washer at any given x value and then add them all up. Stack them up from 1 to 4. Okay, so I draw my representative rectangle. Just put it anywhere because it's just as representative of n of them. I'm going to actually put n of these from 1 to 4, rotate them all, and add them all up. So, but I only have to draw one just to picture what's going to happen. So we're going to put this at a value of x. The width of this thing is delta x. And the height, right, is the square root of x, because that's the function that we're going up to the height of. So when I rotate it around the line y equals -2, I end up with a washer. And how would you find it's got a thickness? Someone's going to have to teach me how to draw this. Thickness of delta x. I need to know the volume of this thing, right? So the volume of something that is has uniform thickness is just the area of the base times the height. So the volume of my washer is the area of the base times delta x, the height. So how would I find the area of that washer? What do I need to know? Yeah, I can find the area of the outer circle, subtract the area of the inner circle. Okay, so to find the area of the outer circle, I need to know that distance, a large radius. Okay, so I go back to my picture and try to figure out where that distance comes from, right? So this is the center of my washer, the axis of revolution, and the outer radius goes up to the curve. So how far is that? This is the line y equals -2. Square root x minus -2 or +2. Put that in my diagram. So this is the square root of x +2 or minus -2, right? Whenever you're finding the distance between 2 points on a number line, you just subtract them. Minus -2 becomes +2. All right, and then what's my inner radius? Just 2. think it's just 2, right? It's the distance from, this is the center, to the edge of my area. This is my inner radius, 2. Sometimes it helps people to visualize this if you draw the reflection of your region down below. Like you can't actually draw it coming out of your paper, but you can draw what happens when after it's rotated 90 degrees, and that can help you figure out what the radii are. So let me just do that. So when I rotate this, it's going to end up over here. You just do a reflection. So imagine it coming out of the board, rotating around the axis of revolution, and after it's gone 180 degrees, it's going to be down here. Right? So this can help you figure out what your inner and outer radius are. So your inner radius is this 2, and your outer radius is this pink x plus 2, square root x plus 2. Okay, so the area of my washer is, we'll call it pi big R squared minus pi little r squared. Because that's the area of the big circle minus the area of the little circle, and then times delta x. And now I know what big R and little r are. Radical x plus 2 and 2. So why did I write plus? I don't know. Okay, so there is the volume of one single washer, one representative cross section of the region I'm trying to find the volume of. So now I have to add them all up. Now I'm going to add a whole bunch of these things that I get. I'm going to start at 1, I'm going to go to 4, I'm going to do n discs. Go to a new page. So the area of my region is approximated by adding n of these discs together. And each disc has volume pi times square root x plus 2 squared minus 4 pi delta x. So I just take that one disk and I say, okay, now I'm just going to add a whole bunch of these things together. I should have called this an x sub I guess. And then I'd let n go to infinity. Take the limit as n goes to infinity, and it becomes an integral. The delta x becomes a dx. How would I actually take this integral? Any ideas? Oh yes, thank you. I need the bounds. 1 to 4. Spoil it out and break it up using power rule. Yeah. So I think actually the first thing I'm going to do is pull out a pi. So that is gone and that is gone. And then I'm going to FOIL radical x plus 2, square the first and I get x, square the last and I get 4. Take the product of the 2 root x, and double it. And then I have minus 4 dx. That came from right here after I pulled the pi out. Okay, so my 4's cancel. And we can now just use the power rule. Okay, so the antiderivative of x is x squared over 2. Antiderivative of root x would be add 1 to the exponent and you get 3/2. So we're going to have an x to the 3/2. And then you'd have to multiply by 2/3. 4 times 2/3 is 8/3. Evaluated from 1 to 4. Okay, so if I plug in 4, I get 16 over 2 is 8 plus 4 to the 3/2 is 2 cubed is 8, 64/3. And then I plug in a 1 and I get a 1/2 plus 8/3. Not in the right frame of mind to do this in my head right now. I'll get it wrong. Eight plus 64/3 minus a 1/2 plus 8/3. It's 157 over 6, and then times the pi. All right, what do you guys think? Is it okay? Overwhelming? No response. Okay. Good talk. Okay, so do another one. New function this time. Okay, I want to find the volume of the solid generated when the region between the graphs of 1/2 plus x squared and x is revolved about the x-axis over the interval from 0 to 2. So I have to graph both functions to figure out what my region is. Use your graphing calculator if needed. If I put this on a test, I will most certainly give you functions that you know how to graph, supposedly, right? Like a vertical shift of x squared, not difficult to graph, right? Something like, or a line, like in this case. Okay, so 1/2 plus x squared is a parabola that goes like that. And the line y equals x goes like that. And they would cross when the two functions are equal. I'll just have my calculator tell me where they cross instead of using the, I'll put the quadratic formula in here. So negative b plus square root of b squared minus 4 times a times c. They don't cross. Okay, I drew it wrong. That goes like that, and that goes like that. There we go. Okay, so now I'm going to look from 0 to 2, the region between these two graphs. So 0, here's 2. So this is my region that I'm going to rotate about the x-axis. What are my cross sections going to look like? Washers, yeah. Except for this one at the very end, it'll be a disc, right? So just pick a random spot in here to look at a cross section, somewhere in the middle, and draw a little representative rectangle. And we're going to see what the volume of that thing is. And we rotate that rectangle around the x-axis. And then I'm just going to add up a whole bunch of those things. So again, it can help you picture what's happening. If you draw the reflection, like you have to imagine this coming out of the board, rotating around the x-axis, and when it gets down after 180-degree rotation, you can draw what it looks like there. So it would be the reflection. That and that. That was terrible. Is that what it looks like? No. There we go. Good enough. So there's a reflection after 180 degrees. I'm putting that little rectangle at a random x sub I somewhere between 0 and 2. Random x sub I somewhere between 0 and 2. Okay, so it comes out of the board, it rotates around, 180 degrees later, it's down here. So the thing that it's creating when it rotates is a washer. Okay, and then we have to figure out the radius, the outer and the inner radius of this washer. So the center of my circle is the axis of rotation, and the outer radius would be this distance, which is what? ½ plus x squared. Yeah. So it's the curved function. It's the distance from the x-axis up to the curved function. And you can find that by taking your x and plugging it into the curved function, right? It's ½ plus x squared. So my outer radius, ½ plus x squared. And then my inner radius is this distance. And what is that? It's just x, because that's the line y equals x. So then I find the volume of my disk, which is pi r squared minus pi r squared. And then the width of the depth or the height or whatever dimension you want to call it, the third dimension of the disk is delta x, the thickness of the disk. Okay, so I have pi times my outer radius, ½ plus x squared squared, minus pi times my inner radius, x squared, and all that times delta x. Volume of one cross-section disk. Then I need to add these all up. So the volume of my whole region is approximately the sum of a bunch of n of these rectangles. Go from I equals 1 to n, where I add up n disks that have this volume. Pi times ½ plus x squared squared. Minus pi x squared delta x. So I'm going to make n of these rectangles, each one at a different x sub I, from starting at x1 to xn. x1 will be at 0, and xn will be at 2. So the exact volume of my region is what I get when I let n go to infinity, and that becomes an integral from 0 to 2 of pi minus pi x squared dx. Okay, so then we just, when you go from a sum to an integral, the delta x becomes a dx, right? In the limit, because delta x is a width, right? And dx represents sort of an infinitesimally small width. All right, so I'm going to do the same thing as before. I'm going to take out a pi, I think. And then I'm going to FOIL this, square the first, square the last, take the product of the two, 1/2 x squared, and double it. And you get plus x squared. And then I have a minus x squared. Oops. Dx. The x squareds cancel. And then taking the antiderivative is easy, because this is just a power rule. Pi times 1/4 x plus x to the 5th over 5, evaluated from 0 to 2. All right, when I plug in a 2, I get 1/2 plus 2 to the 5th is 32/5 minus, plug in 0, I get 0. 1/2 plus 32/5. 6.9? 6.9, I think. Yeah, okay, good. All right, so I gave you some formulas, right? And I wrote it down. I wrote down the disk method formula earlier. I didn't highlight it. It's the pi times the integral of the function squared, because your function is your radius, right? So this says pi times the radius squared, and then you add up an infinite number of these guys. Okay, and then the washer method is pi times an integral of f of x squared minus g of x squared. F of x being your outer radius, g of x is your inner radius. So I don't ever remember these guys. I always start from a picture, draw the cross section, and come up with a formula, right? But if you're a formula person, you can use this. All right. So we can equally well spin things around vertical axes of revolution instead of horizontal. So I can spin things around, say, the y-axis. I could find the volume of the solid generated when we take this same region under square root x between 0 and 2 and revolve it around the y-axis. Actually, it's not the same region. Sorry, I'll draw it. Okay, so I have square root x. Y equals 2 is up here. And x equals 0 is the y-axis. No, yeah, it's the y-axis. Sorry, that's not where y equals 2 is. Here's the line y equals 2. So this is my region. Same region as before, but I'm going to revolve it around the y-axis. No, that's x equals 2. That's x equals 2. Sorry. Yeah. So if this is 2, this would be a 4. Not that it matters, but. So this is y equals 2. X equals 0 is the y. Oh, wait. X equals 0 is the y-axis, right? Yeah. So this is my region. And I'm going to take that region, spin it around the y-axis. Okay, so I need to look at what the cross sections look like. So instead of using a vertical rectangle, I'm going to use a horizontal rectangle. I'm going to take a slice this way. And its width, it's going to be at a height of y, and its width is delta y. And I'm going to rotate it around the y-axis, and I'm going to get a disk. And this has got width delta y, which means I need everything to be in terms of y. So if I pick a random y value and go down to the x-axis, what's the x value? It's the well, yeah, it's the radius, but what specifically is it? Y squared, yeah, right? Because I remember when y is 2, the x-axis on the x value that would give that in the function square root x would be a 4, right? So you take the y value and you square it. So the distance from the y-axis to the curve, if you know the y value, is y squared. And you can get that by starting with the formula. You have y equals the square root of x. And you say, well, that's what I would do if I know x and I want to know y. If I know y and I want to know x, solve for x, right? Square both sides. X is y squared. Okay, so the volume of this disk is going to be pi times the radius, which is y squared, times delta y, or pi y to the 4th delta y. Then I'm going to add a bunch of these things up. I'm just going to have all these little rectangles, n of them, rotate them all around the y-axis, and add up their volumes. So the area of my region will be approximately the sum of pi yi to the 4th delta y. Then take the limit as n goes to infinity, and you get an integral of pi y to the 4th dy. Delta y becomes a dy. And what are my bounds of integration going to be? 0 to 2, because that's where I'm stacking up these cross sections, starting at 0 and going to 2. And they should be y values because everything is in terms of y. So I have pi times y to the 5th over 5, evaluated from 0 to 2, which is 32 pi over 5.
Solve for this by just turning it in order and solve line would be the same, right? Swap x and y.
Sure. Yep. Yes, you could use, if you turn this whole thing 90 degrees, this would be the function x, y equals x squared. Yeah, you can do that. Okay, So if you're into memorizing things, this should help you set up your integrals. If your slice is vertical, your equation should be, solve your equation for y, and the integral will be of the dx variety, right? Vertical slices, dx integral, your variable should be x. So Vin-Dixie, vertical dx. Horizontal slices, you're going to solve your equation for x, and your integral will be of the dy variety. Howdy. Horizontal dy. Here's a neat little website that you can easily create your own solids of revolution. You know, just pick any functions you want and watch them revolve and create cool looking solids. Check it out sometime if you want. And now I want you to try some problems.